My name is Avi, and I'm a PhD student at UC Berkeley. Today, I'll be talking about some of our recent work on incorporating large prior datasets to extend and generalize skills learned via RL. Consider a robot that has been trained using reinforcement learning to take an object out of an open drawer. It learns to grasp the object and pull it out. Now, if this robot is placed in a scene where the drawer is instead closed, it will likely fail to take the object out, since it has not seen this initial condition or scenario before. How can we learn policies using RL that can generalize to new initial conditions? In our example, a simple new initial condition might consist of a closed drawer, while more complicated new initial conditions consisting of the drawer being blocked by an object or by another drawer are also possible. We would like to enable our policy to execute the task from as many different initial conditions as possible. In this paper, we propose to extend skills learned via RL through use of prior datasets. While the task-specific dataset consists of behavior relevant for the task, the prior dataset can consist of a number of random or scripted behaviors being executed in the same environment. If a subset of this prior dataset is useful for extending our skill, we can leverage it for learning a policy that can execute the task from new initial conditions. Note that not all prior data needs to be useful for the downstream task, and we don't need this prior dataset to have any explicit labels or rewards either. We can now formalize our problem setting. The input to our method consists of two distinct types of datasets. The first dataset is a task-specific dataset and is labeled with sports rewards, similar to standard RL. The second dataset consists of unlabeled interaction data with no associated reward labels whatsoever. This dataset need not contain any interactions with the task object of interest, and not all of this data needs to be useful for the downstream task. Our goal is to utilize both prior data and task-specific data to learn a policy pi that can execute the task from initial conditions that were unseen in the task data. In this paper, we primarily focus on an offline reinforcement learning setting, making use of only previously collected datasets. We start by running Q-learning on the task data, which allows for Q values to propagate from high reward states to states that are further back from the goal. We then add the prior dataset to the replay buffer, assigning all transitions a 0 reward. Further dynamic programming on this expanded dataset allows Q values to propagate to initial conditions that were unseen in the task data. Running reinforcement learning now results in a policy that can solve the task of interest from new initial conditions. Note that there is no single trajectory in our dataset that solves the entire task from these new initial conditions, but Q-learning allows us to stitch together relevant trajectories from prior and task data without any additional supervision. Let us first visualize the policies learned without any prior data. We see that the policy is able to successfully execute the task from initial conditions that were seen in the training set, but fails to solve the task for unseen initial conditions. We now visualize the performance of the policy learned by our method. We see that, in addition to solving the task from seen initial conditions, the policy is also able to execute the task from unseen initial conditions, which indicates that our method is successfully able to leverage our unlabeled prior data. We compare our method to previous works that incorporate prior data, such as initializing from behavior cloning. We see that for novel initial conditions, such as where the drawer is blocked by an object, only our method is able to consistently solve the task. There is a comparison between our method and previous works for another new initial condition, where the bottom drawer is blocked by the top drawer from being open. Once again, our method is able to consistently solve the task. Here is a summary of our results, where we see that our method is the only one that is able to obtain a high success rate for all unseen initial conditions. While we were able to obtain success rates of around 70% from offline training alone, our method is also amenable to online fine-tuning. We see that for all of the novel initial conditions for the drawer task, the fine-tuned policy is able to achieve a success rate of over 90%. We also evaluate our method on a real robot, where we see that our learned policy is able to open a drawer and take an object out, even though it never saw a single trajectory executing the entire task during training. Our method succeeds on 7 out of 8 trials, while our strongest baseline based on behavior cloning was unable to solve the task even for a single trial. Here are some example rollouts from our learned policy. Thank you.